Electricity is one of nature's greatest forces. And by the middle of the 20th century, we'd harnessed it to light and power our modern world. Hundreds of years of scientific discoveries and inventions brought us here. But it would take the eccentric genius of one man to unlock the full potential of electrical power. In the winter of 1943, Nikola Tesla looked out across the Manhattan skyline for the very last time. Tesla had been born into a world powered by steam and lit by gas. But before his eyes, he saw a new world, a world transformed, a world powered by electricity. His world. Frail, lonely, and still mourning the death of one of his beloved pigeons, this extraordinary and eccentric genius knew that his life's work was done, and he lay back on his bed to die. It would be 3 days before anyone found his body. Just over 200 years ago, early scientists discovered electricity could be much more than simply a static charge. It could be made to flow in a continuous current. But they were about to discover something profound, that electricity is connected to magnetism. Harnessing the link between magnetism and electricity would completely transform the world and allow us to generate seemingly limitless amounts of electrical power. This is the story of how scientists and engineers unlocked the nature of electricity and then used it in an extraordinary century of innovation and invention. But not before one of the most shocking engineering rivalries in history was finally laid to rest. Our story begins in London at the beginning of the 19th century with a young man who would further our understanding of electricity as much as any other. On the 29th of February 1812, a 20-year-old self-educated bookbinder called Michael Faraday came here to the Royal Institution of Great Britain. He was surrounded by the great and the good of the academic world, and he was about to listen to one of the greatest scientific minds of the age. Faraday, the son of a blacksmith, had finished his formal education when he was just 12 years old. He would never get to university, but he wasn't finished with learning, as he was fascinated by science. Faraday worked long and hard during the day binding books, but in the evenings he would read whatever scientific literature he could lay his hands on. He loved learning new things about the world, and he had this constant desire, this passion to understand why things were the way they were. Reading scientific papers was one thing, but to really satisfy his craving for knowledge, Faraday was desperate to see the experiments themselves. And he eventually got his chance when he was given a ticket to attend one of the last lectures of England's greatest chemist of the time, Sir Humphrey Davy. It was to change young Faraday's life forever. After watching Davy, awe-inspired and full of ideas, Faraday knew what he wanted to do with his life. He was determined to dedicate himself to furthering science. And that's just what he did. Within a year, Davy had appointed him as an assistant at the Royal Institution. With Davy as his patron and, well, his boss, Faraday studied all manner of chemistry. But what would inspire his greatest breakthroughs were the invisible forces of electricity and magnetism. In 1820, both were being studied by a Danish scientist, Hans Christian Ørsted, who'd made an extraordinary discovery. He passed an electric current through a copper rod and brought it close to a magnetic compass needle and saw that it made the needle rotate. To Ørsted, it was remarkable. He'd shown for the first time that an electric current can create a magnetic force. He'd bound electricity and magnetism together. Today, we call it electromagnetism, and it's one of the fundamental forces of nature.
Ørsted's discovery sparks off a whole new spate of inventive activity around and about the fields of electricity. You can almost see electrical experimenters vying, competing with each other to find new links between electricity and the other powers of nature.
At the Royal Institution, Faraday set about recreating Ørsted's work, which would mark his first steps to fame and fortune. And through his rigorous research, he concluded that there must be a flow of forces acting between the wire and the compass needle. The device he designed to demonstrate it would change the course of history. Faraday created a circuit using a battery like this, a pair of wires, and a mercury bath. Now, the circuit carries on through these copper posts, and this wire hangs freely, it dangles into the mercury. Now, because mercury is such a good conductor, it completes the circuit. When the current runs through the circuit, it generates a circular magnetic force field around the wire. Now, this interacts with the magnetism from a permanent magnet that Faraday had placed in the middle of the mercury. Together, they forced the wire to move. Faraday had proved that this invisible force really does exist, and he could see its effect: circular motion. This beautiful device was the first to convert electric current into continuous motion. Basically, it's the earliest ever electric motor. But Faraday was about to take this experiment further.
One of the lasting effects of Faraday's discovery of electromagnetic rotations in 1821 was that it showed that there was a relationship of some sort between electricity, magnetism, and motion.
Faraday explored this relationship in detail and set himself an even more difficult challenge: to use magnetism and motion to make electricity. Eventually, his obsession, hard work, and determination paid off. The breakthrough came on the 17th of October, 1831, when Faraday took a magnet like this and moved it in and out of a coil of wire. He was able to detect a tiny electric current in the coil moving one way and then the other. Faraday knew he was onto something. A few days later, instead of moving the magnet through the conducting wire coil, he set up the equivalent experiment by moving a conducting copper plate through the magnetic field. He didn't know it at the time, But as his spinning disk cut through this magnetic field, billions of negatively charged electrons were deflected from their original circular course and began to drift towards the edge. A negative charge built up at the outer edge of the disk, leaving a positive charge at the center. And once the disk was connected to wires, the electrons flowed in a steady stream. Faraday had generated a continuous flow of electric current. Unlike a battery, his current flowed for as long as his copper disk was spun. He'd created electrical power directly from mechanical power.
Although Faraday's discovery of induction was extraordinarily important in its own right and had profound effects for the understanding of electricity and technology for the rest of the 19th century, for Faraday, what it did was to open up a decade of powerful research because it gave him the clue about how he should pursue his research.
While Faraday continued his work trying to understand the very nature of electricity, inventors from across Europe were less interested in the science and more interested in how electricity could make them money.
What's actually quite remarkable, certainly from a contemporary perspective, is that by and large, nobody really seems to care very much what electricity is. You don't have great theoretical debates as to whether it's a force or a fluid or a principle or a power. What they're really interested in is what electricity can do.
Faraday, living in a world of steam power, was informing the scientific community about the nature of electricity. But at the same time, another breakthrough in how we could actually use it had been made. This will be the first device that really brought electricity out of the laboratory and into the hands of ordinary people. The telegraph. The key to understanding the telegraph is understanding a special kind of magnet, an electromagnet. Basically, a magnet created by an electric current. The first electromagnets were developed independently by William Sturgeon in Britain and Joseph Henry in America. And just as Faraday had discovered that by coiling his wire, he could increase the current in it produced by the moving magnet, so Henry and Sturgeon discovered that by adding more coils in their current-carrying wires, they could make a more concentrated magnetic field. Basically, the more coils, the more turns, the stronger the magnet. So if I pass a current through this electromagnet, you can actually see the effects of the magnetic field. This is the standard school experiment of sprinkling iron filings on top of the magnet. If I give it a tap, see the iron filings follow the contours of the field. This allows us to visualize the effects of magnetism. To make an electromagnet even stronger, Henry and Sturgeon discovered that they could place certain kinds of metal inside the electromagnetic coil. The reason iron is so effective is fascinating because you can think of it as being made up of lots of tiny magnets, all pointing in random directions. At the moment, this is not a magnet. The tiny magnets inside are aligned similarly to these compass needles. If you see, they're all pointing in different directions. But when you apply a magnetic field, they all align together. They all combine, these magnets, and cumulatively they add to the strength of the electromagnet. So what Henry and Sturgeon did was place 2 electromagnetic coils on each arm of their horseshoe to create something that was many, many times more powerful. And we can see the power of this horseshoe electromagnet. If I turn it on and use something slightly bigger than iron filings, these small pieces of iron, look at the strength of the magnetic field holding them in place. What's important to remember, of course, is that this electromagnet only works all the time there's a current passing through it. As soon as I turn off the current, the magnetism disappears. Early experimenters showed off this power by lifting metal weights. Henry even made one big enough to lift 1.5 tons of metal. Impressive, but not world-changing. But place that magnet much further away, at the end of a wire, and suddenly you can make something happen at your command, in an instant. This ability to control a magnet at a distance is one of the most useful things we've ever discovered.
If electricity can be made visible a long way away from the original source of power, then you've got a source of instantaneous communication.
By the middle of the 1840s, Samuel Morse had developed a messaging system based on how long an electrical circuit was switched on or off. A long pulse of currents for a dash, a short burst for a dot. This allowed messages to be sent and received by using a simple code.
Contemporary early Victorian commentators reflect on the fact that electricity and the telegraph is literally making their world a smaller place. You very often get a sort of rhetoric throughout the 19th century when people are talking about the telegraph about how more communication, more understanding will render war obsolete because we'll all understand each other better. I mean, retrospectively, it seems hopelessly utopian.
By the 1850s, Europe and America were crisscrossed with land-based telegraph wires. But the dream of instant global communication was frustratingly out of reach. This was because there was still no cable capable of carrying messages between two of the greatest powers on Earth, Britain and America. Many experts were convinced that a working Atlantic cable was impossible. But those who disagreed knew that if they could solve this problem, it could make them serious money. And in the 1850s, American businessmen and British engineers joined forces to prove this could be done. Attempt after attempt ended in disaster. The heavy cables kept snapping in heavy seas and storms. Finally, on the 29th of July, 1858, two parts of a cable were spliced together in mid-Atlantic. You see, a single cable was simply too big to have been carried by one ship. Then one end was taken to Newfoundland and the other end to southwest Ireland. 6 days later, the first direct link between the two most powerful nations in the world was in place. The project was hailed a huge success, and a formal message of congratulations was sent from Queen Victoria to President Buchanan. But before the celebrations were over, things started to go very wrong. This is Chief Engineer Bright's original notebook. You can see here Queen Victoria's original message. Now, it's only 98 words long, but it took 16 hours to transmit. The telegraph operators on the other side found it very hard to decipher the message. The electrical signals that they were receiving were blurred and distorted, and they kept asking for words to be repeated over and over again. So you can see here, repeat after sending, waiting to receive, no signals. Clearly, transmitting across the Atlantic wasn't going to be as straightforward as people had hoped. Over the next few days, several hundred messages were exchanged. But those arriving in Newfoundland became almost impossible to decipher. Just a jumbled mess of dots and dashes. There was a serious problem with the cable, and it was getting worse. Well, the 1858 cable was never fully repaired, and the end finally came when British engineer Wildman Whitehouse mistakenly believed that by increasing the signal voltage, he could force the messages through to Newfoundland. The cable simply stop working altogether. At the time, increasing the voltage by using more powerful batteries made sense. Most experts believed electric current flowed through a cable like a fluid in a pipe. Increasing the voltage was the equivalent of increasing the pressure in the system, forcing the current through to the other end. But the telegraph was actually carrying pulses or ripples of current along the cable, not a continuous stream. And over long distances, these pulses were becoming distorted, making it difficult to tell what was a short dot and which was a longer dash. By studying the effectiveness of underwater cabling, scientists were beginning to understand that electric current didn't always flow like water, but was also creating invisible electromagnetic waves or ripples. And it's this breakthrough that would lead to a new branch of research into the electromagnetic spectrum and solve the problems of the Atlantic telegraph. In effect, the transatlantic cable was a giant, ambitious, hugely expensive experiment. The failure of science to keep pace with technology had been exposed, and a new, more theoretical, and for me, much more exciting approach to understanding electricity began to unfold. Armed with this new understanding of how electric pulses actually moved along the cable, improvements were made to its composition, design, and how it was laid. It would take another 8 years of scientists and engineers working together before a working cable was finally put in place. And on Friday, the 27th of July, 1866, a message was sent from Ireland to Newfoundland, clear and crisp. A treaty of peace has been signed between Austria and Prussia. At last, the dream of instant transatlantic communication had become a reality.
The success of the 1866 cable makes the world a smaller place, yet again. The change from a world where it took days or weeks or months for information to travel, to a world in which information took seconds or minutes to travel, is far more profound, I think, than anything that's taken place during my lifetime.
The invention of the telegraph changed ordinary people's lives. But it would be the breakthroughs in how we used continuously flowing electric current that would have an even greater impact. Because inventors were developing a new way of using electricity. To make something every person in the world would want. Electric light. Until the 19th century, we only knew of one way to make our own light: burn things. And by the middle of the 19th century, we'd perfected a very effective way of lighting our homes, using gas. A typical British home in the 1860s would have been lit like this. Highly flammable gas would have been pumped directly into people's houses through a network of pipes. But these gas lamps were too dull for large outdoor areas. So railway stations and streets began to be lit from a more powerful source: electric arc lights. The first arc lights were demonstrated by Michael Faraday's mentor, Sir Humphrey Davy, at the Royal Institution as early as 1808, and they worked by passing a continuous spark of electricity across two carbon rods. But their intense white glow was just too bright for people's homes. For an electric light to compete with gas, it would need to be subdivided into many smaller, less powerful and more gentle lamps. Whoever succeeded in bringing electric light to every home in the land was guaranteed fame and fortune. And by the early 1880s, the most famous, most prodigious, most fiercely competitive inventor in the world had taken on the challenge: the American Thomas Alva Edison.
For Edison, invention was a passion. It's what he loved doing. He loved being in the laboratory. The first thing that drove that passion is that it was a lot of fun for Edison. I think that was the thing that he found most exciting, is that this was something he did well, and it allowed all of his creativity to come to the fore.
Edison is Mr. Electrical Invention. He's the man they trust. He's the man that they think can do anything. He's also the man who has his carefully cultivated connections with entrepreneurs, with people who are willing to put their cash where Edison's mouth is, so to speak, and back him in this sort of venture.
For Edison, the money was probably the least important reason. For Edison, the money was important for one reason: to allow him to do the next project.
Edison had assembled a group of young and talented engineers at a cutting-edge laboratory in New Jersey, 26 miles from Manhattan. Menlo Park would become the world's first research and development facility, allowing Edison's team to invent on an industrial scale.
They worked incredible hours. You know, one of them talked about how he hardly ever saw his children because he was in the lab all the time. But they knew they were in the midst of something really important, right? That if Edison succeeded, right, if they succeeded with Edison, that their futures were secure.
Edison's dream was to bring electric light to every home in the land. And with his team of engineers behind him and the vision of an electric future ahead, he launched his campaign. The race to bring electric light to the world was to play out in the great cities of the time: New York, Paris, London. Edison's Menlo Park team set about developing a totally different form of electric lamp: the incandescent light bulb. In fact, Edison's light bulb design wasn't all that new or unique. French, Russian, Belgian and British inventors had been perfecting similar bulbs for over 40 years. And one of them, an Englishman, Joseph Swan, had been developing his own version of an incandescent lamp. Both Swan and Edison's light bulbs work by passing an electric current through a filament. Now, a filament is a material in which the electric current flows through with more difficulty than it does through the copper wire in the rest of the circuit. And it relies on the idea of resistance. Now, inside this jar, I have a filament made out of ordinary pencil lead, and we can see what happens as I pass a current through it. Down at the atomic scale, the atoms in the filament impede the flow of electricity, so it takes more energy to force it through, and this energy is deposited in the filament as heat. Now, as it heats up, its resistance goes up, which again raises its temperature until it glows white hot. Now, one of the first materials Edison used for his filaments was platinum. With its relatively high melting point, platinum could be heated to a white-hot temperature without melting. It could also be stretched into thin strands, and the thinner the strand, the more resistance it offered to the current passing through it. but platinum was expensive and didn't offer enough resistance. The race was on to find a better alternative, and the solution came when the Menlo Park team switched to a method Swan was also developing, using a vacuum to stop cheaper carbon filaments from burning up too quickly. Edison and Swan tested all kinds of different materials for their filaments, everything from raw silk and parchment to cork. Edison even tested his engineer's beard hair. Eventually, he settled on bamboo fibre, while Swan used a treated cotton thread. Edison and Swan's light bulb designs were very similar. Eventually, they came to an agreement and went into partnership to sell light bulbs in the UK. Today, many people still believe that Edison alone invented the light bulb, while Swan has become a footnote in history. But his incandescent bulb was only part of Edison's strategy. He'd also invented an entire electrical system of sockets, cables, and meters to go with it. And being a brilliant businessman, he'd developed a groundbreaking new way of distributing electricity. Edison knew that the key to making money from his system was to generate the electricity in a central station and then sell it to as many customers as possible. It seems obvious to us now, but until then, anyone who wanted to use electricity had to have their own noisy generator to make it. Edison's ambition was huge. He wanted to light the fastest growing and most exciting city in the world. New York. In the summer of 1882, Edison stood in a unique position at the center of 19th century science and invention. He'd patented a cutting-edge incandescent light bulb. He'd amassed an unprecedented knowledge of electrical engineering. And above all, he'd cultivated a reputation among the American public of being such a genius inventor that journalists hung on his every word. And the financial muscle of Wall Street was quick to throw itself behind his new ideas. His vision to electrify Manhattan, and then of course the rest of the world, was seemingly within his grasp. Because Edison and his team were about to launch their most expensive and risky project yet. America's first power station generating continuous direct current. Just before 3 p.m. on the 4th of September 1882, Thomas Edison, surrounded by a gaggle of bankers, dignitaries and reporters, entered J.P. Morgan's building right behind me, flicked one of the Edison patented switches, and 100 of his incandescent bulbs began to glow. Turning to a nearby journalist, he said, "I have accomplished all that I've promised." Half a mile away on Pearl Street, Edison's new power station, costing $500,000 and 4 years of hard work, had sprung into life. The current surged through buried cables, stretching out in each direction. Of course, it might seem obvious to us now, but in New York back in the early 1880s, the idea of burying electric cables underground seemed like an unnecessary expense. This street would have been crisscrossed with hundreds of cables used for telegraphs, telephones, and arc street lighting. Looking up, you'd have seen a tangled mass of black spaghetti blocking out the light. Edison knew this dangerous situation had to change, and for him to make as much money as he could, electricity needed rebranding. It had to be considered safe.
So Edison is arguing both for the greater safety of his DC low voltage system and for underground lines. He can argue that he has a much safer system than electric arc light for streets or gas lighting for indoor lighting, right? He doesn't have to worry about fires, doesn't have to worry about electrocution, that all of this is much safer because of the system he's created with this underground system.
Burying every cable was not only very expensive, but was a logistical nightmare, because this was one of the busiest square miles in the world. Edison chose this area for a reason. Wall Street. Rich, important, influential. Because for Edison's system to make money, all these wealthy customers had to be within a mile of his power station. And this was because Edison calculated the thickest cable he could afford would only carry an adequate amount of his continuous direct current to customers within this range. This was a huge leap forward, because for the first time, dozens of customers could be supplied by just one power station. But there was a big problem. Edison's network could never be economical in lighting America's new suburbs. They just didn't have the concentration of customers needed to make building these expensive power stations worthwhile. Had we stuck with Edison's way of generating and distributing electricity, the world would be a very different place. We'd have to have power stations scattered around no more than a mile apart, even in the centres of our towns and cities. And it would be extraordinarily expensive to even provide power for smaller communities. But someone who held the answers to these problems was about to enter the story. Someone who would help create the modern world and who'd play an integral part in one of the biggest fallouts in scientific history. His name was Nikola Tesla, and he was right under Edison's nose. Nikola Tesla was a Serbian inventor who was born in Croatia and who worked for Edison briefly after arriving in New York at the age of 28. European, introverted, a deep thinker. He was everything Edison wasn't.
Edison and Tesla could not be more different in the way that they handled their self-appearance and their manners, and the way that they constructed a public image for themselves. Edison could care less about the clothes that he had on, and if he spilled chemicals on his good Sunday suit, then he spilled chemicals on his good Sunday suit. He was, basically a very kind of slovenly guy. Tesla, on the other hand, even as a young man in his mid-20s, is thinking about his appearance, how he comes across to people, so he cares about his clothes, he cares about his manner, indeed he even cares about how his portraits are taken, and he always wants to make sure that he has a nice three-quarter profile, so you don't see the fact that he has a bit of a pointy chin.
The life and death of Nikola Tesla is one of the most fascinating yet tragic stories of scientific brilliance, cutthroat business, and shocking public relations stunts. The American public may have been wowed by Edison's new direct current power stations, but Tesla was less impressed. He had a dream electricity could be transmitted across entire cities, or even nations. And he believed he knew how it could be done, by using a different type of electric current. Electrical experts knew that the smaller the current sent down a cable, the smaller the losses in it through resistance, and so the longer the cable could be. Tesla proposed using a method of transmitting electricity where the current could be lowered without a fall in the amount of electrical power at the other end. It was called alternating current. Alternating current is exactly that. It's an electric current that alternates between moving in one direction, then the opposite direction very quickly, as opposed to a direct current which moves only in one direction.
Tesla was interested in alternating current because, like other electrical engineers in the late 1880s, he realized that as you raise the voltage of any current that you transmit from point A to point B, it's going to be more efficient to have a higher voltage.
And since the amount of electric power in a cable is its voltage multiplied by its current, increasing the voltage meant the current in the cables could be reduced, and so losses due to resistance would be less.
However, you don't want very high voltages on the order of, say, 20,000 volts coming into your home. So you need to step down the current that is being transmitted over a distance into your home, and to do that you need a converter or a transformer. Alternating current allows you to use a transformer to make that switch from the high transmission voltage to the lower voltage that you're going to use at consumption.
Perfecting the technology to transmit electricity hundreds of miles from where it was generated would mark a huge step towards the modern world. And a wealthy industrial entrepreneur was already developing the solution. His name was George Westinghouse. Westinghouse believed alternating currents was the future, but it had a big drawback. While it was fine for electric light, unlike direct current, there was no practical motor that could run on it, and no one believed there ever would be, apart from Nikola Tesla.
Tesla, as an inventor, liked to say that the first thing you need to do is not to build something, but to imagine it, to think it through, to plan it. And he had what modern-day psychologists would call an eidetic memory. He could basically remember everything that he saw and then visualize it in 3 dimensions. And they often say that the people that have this skill see it about an arm's length away out here, and they see it in 3 dimensions in that space. And all of the indications are is Tesla had that ability.
This is a Tesla egg. It's a replica of the one Tesla used to demonstrate his greatest breakthrough and one of the most important inventions of all time. It showed how rotary movement can be produced directly from an alternating current, crucially one that could be generated thousands of miles away. This was something that had never been done before.
When Tesla was working on the alternating current motor, he was thinking big, and he was not just tinkering with one little component of the motor and saying, gee, if I can make that a little bit better, it will work out. He's actually thinking about an entire system that involves the generator, the wires to the motor, and the motor itself. He's a complete maverick. He's thinking outside the box. He's doing things very differently than any of his fellow contemporary inventors.
Tesla's solution was ingenious. He fed more than one alternating current into his motor and timed them so that they followed in sequence with each other. The first alternating current energized a coil of wire inside the motor, creating an electromagnetic field which attracted the motor's central moving part to it and then faded. The second overlapping current fed the next coil, dragging the moving part around further before it faded, and the same for the third coil and the fourth. The result was a revolving magnetic field strong enough to make the motor, or in this case his egg, spin. Tesla designed an entire electrical system around this, called polyphase transmission. This meant a noisy and smelly power station generating lots of useful alternating current could now be situated away from populated areas.
And for the first time, you can build large power stations wherever you want, on the edge of town or at a waterfall like Niagara, and you can then distribute the power over long distances and serve all the people in a major city or metropolitan center.
Tesla's breakthrough was the last piece of the jigsaw, but he still had to convince the world that his solution was better than the direct current method championed by Edison. Edison continued to roll out his direct current system, building power stations across New York State. But then Tesla met George Westinghouse, the man who could make his dreams into a reality.
In July 1888, Westinghouse made an offer for Tesla's patents, which has become part of the mystery and folklore surrounding the whole Nikola Tesla story, where it's difficult to separate fact from fiction.
Tesla was paid $75,000 for his alternating current patents and offered $2.50 for every horsepower his motors would generate. This should have guaranteed him vast wealth for the rest of his life, but that isn't what happened.
It's clear to us now that at the time, the AC system was a much better method of transmitting electric power. And you'd think that with Tesla's breakthroughs, nothing could stand in the way of the success of AC over DC.
But one man still believed totally in his direct current inventions. From the filaments of the bulbs to the switches, sockets, and generators. And he wasn't about to waste millions of dollars on changing them. Edison.
The battle lines were drawn. Westinghouse and Tesla went toe-to-toe with Edison for New York's lucrative lighting contracts. Two completely different systems battling it out for one ultimate prize. The chance to light up America and then the world. It would become known as the War of the Currents.
Both camps tried to undercut each other on cost, but Edison believed his beloved direct current was better than alternating current because it was safer. Touching an Edison cable with its low voltage was painful but relatively harmless, whereas alternating current cables carried a much higher voltage, and touching them could be deadly.
So, what Edison was trying to do was to, again, define his DC system, right, as the safe system. It's better than electric street arc lights. It's better than gas, and it's now better than high voltage AC incandescent lighting, right? It's the system that's safe. You adopt the Edison system, you can be sure it's going to be safe.
Edison claimed that AC was a more dangerous type of current than DC, and he highlighted every accident to Westinghouse's workmen and every fire caused by short circuits. It was a potent message because in the 1880s, many people were still terrified by electricity. It could shock and even kill in an instant, and the reasons why still weren't fully understood. For many, the idea of piping this invisible killer into their homes was utterly ludicrous. So the weapon used in the War of the Currents was fear.
And a little-known electrical engineer, Harold P. Brown, was about to take the fight against AC to a whole new level. It was to prove one of the most extreme and negative publicity campaigns in history.
Brown had devised a unique and theatrical way of demonstrating the deadly power of AC, and he was eager to share it with the world. So on a warm summer's evening in July 1888, he gathered together 75 of the country's top electrical engineers and reporters to witness a spectacle they would never forget. Brown's plan was extremely macabre. He'd paid a team of street urchins to collect together stray dogs roaming Manhattan. Out on stage, he addressed his audience. I have asked you here, gentlemen, to witness the experimental application of electricity to a number of brutes. His demonstration involved electrocuting the dogs with DC and AC power in an attempt to show that AC current killed them more quickly. And it wasn't just dogs. Brown went on to make public spectacles of killing a calf and even a horse. And he moved from dogs to larger animals for a reason. He wanted to show that the AC form of electricity was so dangerous it could kill any large mammal, including humans. Brown's animal experiments had persuaded American politicians the most humane method of executing condemned criminals should be with alternating current generated by Westinghouse machines. Edison's lawyers even suggested a new term to describe being electrocuted in this way: to be Westinghoused. And at precisely 6:32 on the morning of the 6th of August 1890, a 45-year-old man, William Kemmler, was strapped to a wooden chair and 2 soaking wet electrodes were carefully attached to him. And as 26 officials and doctors looked on from an adjoining room, Kemmler said goodbye to the prison chaplain and waited.
The execution of William Kemmler marked the lowest point in the War of the Currents, but it wouldn't quite mark the end, because Nikola Tesla was about to do something that had never been seen before, something so wondrous and daring that it would live on forever in the memories of those who saw it.
Tesla had been developing a method of generating very high-frequency alternating currents. And on May 21st, 1891, at a meeting of top electrical engineers, he demonstrated it.
In an almost magical display of awesome power and wonder, and without wearing any safety chainmail or mask, tens of thousands of volts produced by a Tesla coil passed across his body and through the end of a lamp that he was holding.
Tesla's alternating current was at such a high frequency that it passed through his body without causing serious harm or even pain. His demonstrations showed that if handled correctly, alternating current at extremely high voltages could be safe. The war of the currents had been won by Westinghouse and Tesla. In 1896, a new power station was completed at Niagara Falls, using Westinghouse AC generators to produce Tesla's polyphase current. Finally, huge amounts of power could be transmitted from the falls to nearby Buffalo. And then, a few years later, the Niagara plant was providing power to New York City itself. And today, almost all of the electricity generated in the world is done so using Tesla's system.
But Tesla's story doesn't end in fame and fortune.
Although he went on to make significant contributions to many other areas of science and invention, to save George Westinghouse from ruin after a stock market crash, he gave up his claim to the royalties from his polyphase inventions.
Nikola Tesla was a uniquely talented man, and we owe him so much. But he was also hugely complicated, and sadly, later in life, he became more and more troubled. He was fixated with the number 3, counting it out loud as he walked, and he developed strange phobias with germs, and with women wearing pearl jewellery. In many ways, his brilliant mind simply spun out of control. As Tesla's life unravelled, he withdrew from people and found emotional comfort elsewhere. He became obsessed with pigeons and was regularly seen feeding them here in Bryant Park in the centre of Manhattan. He even fell in love with one particularly unusual white bird, and when it died, he was left heartbroken.
As an old man, Tesla was left almost bankrupt and alone, living as a semi-recluse in this hotel. His last years were spent here in room 3327 of the New Yorker hotel, sad, confused, destitute. Edison went on to become an American hero, and his company would form part of General Electric, even today one of the world's biggest multinational corporations. In January 1943, the story of Nikola Tesla was coming to an end. But looking out across the Manhattan skyline for the very last time, he saw a sky lit up with twinkling lights and a million lives transformed by his genius.
The ability to generate and transmit electricity and the invention of machines to use it have changed our world in ways we couldn't possibly have imagined.
We can now generate billions of watts of electricity every second, every hour, every day. And whether we do it using coal, gas, or nuclear fission, power stations all rely on the principles discovered and developed by Michael Faraday, Nikola Tesla, and all the other early electrical engineers from an amazing age of invention. We now take electricity for granted and have forgotten how magical and mysterious a force it once was. But there's something we should never forget.
Today, without it, the modern world would collapse around us, and our lives would be very, very different.
In the next episode, we tell of the electrical revelations that led to a revolution in our understanding of this amazing force.
To find out more about the story of electricity and to put your power knowledge to the test, try the Open University's interactive energy game. Go to bbc.co.uk/electricity and follow links to the Open University.
And the story of electricity concludes here on BBC HT at the same time next Thursday. Next this evening, Tracy Emin on Who Do You Think You Are?